Okay, so I'm assuming that the recording has also started. So we can also see the pseudocode of merge sort. We went over the pseudocode, and we have also seen a working example, basically an input instance to the merge sort algorithm, and we have seen how the algorithm works on that small example input. Now it's time to try to analyze the running time of this merge sort algorithm. Let me try to find the pen in here. So let's see. Okay, so note that the merge sort algorithm by its nature is recursive because we make recursive algorithms to smaller inputs on merge sort. So in this first call, for instance, we call our merge sort algorithm recursively to sort the left half of our input instance, and the second one we again call merge sort algorithm recursively to sort the right half of the given input sequence. Now, while analyzing the running time of algorithms that are recursive, one natural starting point is to write a recurrence T of n to describe the running time of such a recursive algorithm in a recursive fashion as well. So let's try to do that. So if let's write it over here. It doesn't really matter. So we will try to describe this T of n, which will tell us the running time of the merge sort algorithm on an input of size n. So how can I describe this T of n? Just by looking at this pseudocode. Any ideas? So this is the main algorithm. The main algorithm is algorithm merge sort. So we start out by constant operation, which is just one comparison, and then another constant operation, which is just some addition, division, and assignment. So this is constant. And we have a recursive call in here. How can I describe the time? We will consider these constant times that we spent over here later on. But let's now try to describe the running time that we spent in this first recursive call. Does anybody have any idea regarding what the running time spent for this recursive call is? Are you all still following? Can you all still hear me? Any problems with hearing or seeing the PDF slides? Okay, so any idea on how to describe time spent for this initial recursive call? Should be easy. If T of n, can you not see? Okay, let's try to make it slightly bigger. I'm trying to make it so that I can see what you type as well. So I need to keep both of the screens on at the same time, but let's try to make this a bit bigger. Can you see better now? Okay, so if T of n is describing the running time of merge sort on sorting n elements, what is the time spent for this merge sort call, which again does the same thing, but with a smaller instance. So our instance size originally is n. Yes, exactly. So the size of the instance for this recursive call is n divided by 2. You're right, Berkay. But what is the time spent for the merge sort? The size of the input, this one's size, the size that we describe here is n divided by 2. And the time spent for this recursive call will be t of n divided by 2 then, right? Because t describes the running time of merge sort, and t of n divided by 2 describes the running time of merge sort on an input of size n divided by 2. We don't note that we don't simply say n divided by 2 for the running time of this. We need to say t of n divided by 2. Is this part clear for everyone? Is this last part clear for everyone? Okay, now if this first recursive call takes t of n divided by 2, this second one also is the same because its input size is also n divided by 2. So the running time spent by the second merge sort call will also be t of n divided by 2. So for both of these two together, we will spend 2t of n divided by 2 running time for these two, plus any running time that we spend for the rest of the code, which is constant time for this part, constant time for the comparison, constant time for this initial line, and we need to find out what is the running time that we spend for this merge call. Initially, when we call merge sort, we have n items. So our merge code will have n items to work with. If it has n items to work with, this merge called, this merge function, how much running time does it require? We need to find that out by looking at the pseudocode or by trying to understand what this merge algorithm does. Remember what the merge algorithm was doing. It has a pointer to the left part of the array, a pointer to the second array A2. This is left part of the original array A. This is right part of the original array A. And we need to combine these two into a single output array A. Okay. First, we were copying the left part into A1, the right part into A2. And then, so how much time does that copying require? This part, basically. If we inspect the pseudocode of the merge algorithm, how much running time do we spend for these two for loops? Yes, it is n. It is theta, some constant times n, basically. Okay, can everybody see that? Because we have n items, we copy basically n divided by 2 items into A1 and n divided by 2 items into A2. So in total, we do almost n amount of time, but each assignment and other things might take constant times. So we say that these two for loops together takes some running time proportional to n. So basically some constant times n. The rest of the time that we spend, so this is constant time, this is constant time. The rest of the time that we spend is for this for loop, this last for loop. How much time do we spend for this last for loop? Any ideas for this? Okay, so Faizenur has a guess that it is n. Yes, it is again proportional to n, basically some constant times n. Let's see why. We need to see why, we need to understand what this last for loop is doing. It compares an element of A1 and an element of A2. Whichever one is smaller, it places into output array A. Yeah. So it does one comparison and then places an element into A. And then it goes on for the next element. If it has taken from A1, it goes on to the next element in A1. It compares these two, and whichever is smaller, it places into output array A and forwards the necessary pointer. So each time that we place a new element into our array A, we are doing only one comparison. And in total, in A, we have n items. Okay, for each item that we place into A, we spend constant time and we have n items. This means that this for loop, the last for loop, will require time proportional to n, basically some constant times n. So this initial Okay, can you hear me now? Yes, at some point I had a slight problem with the internet connection. Anyway, so this two initial for loops requires some constant times and the last for loop requires some constant times n. So in total, we can say that the merge algorithm working on an input of size n will require some constant times n running time. So let's write that in our running time function for the merge sort algorithm. It was 2 times T of n divided by 2 for these recursive calls. And for the merge algorithm itself, it will require some constant C times n. We could write in here plus constant to account for the operation in here and the comparison in here. But since constant times n already is bigger than simply a constant, this accounts for it already. So the recurrence relation describing us the running time of our merge sort algorithm is this. T of n is equal to 2 times T of n divided by 2 plus some constant times n. Is this recurrence relation clear? Is it clear how we have found this recurrence relation? Okay, now that we have found a recurrence relation to describe the running time of the merge sort algorithm, this is not enough to complete our analysis of the running time. Can anybody tell me why? Why is this not enough? Why can't we just leave saying that the running time of merge sort is T of n is equal to 2 times T of n divided by 2 plus Cn? Why can't we just leave it here? We talked about this a little bit yesterday. Does anybody remember? Not worst case and best case. Notice that while writing this recurrence relation T of n, we haven't made any analysis regarding worst case or best case. So let's relook at how we found the running time. So constant time for this assignment, this recursive call is always T of n divided by 2. Right? It doesn't matter how the input is organized because it is calling merge sort on an input of size n divided by 2. Then its running time must be T of n divided by 2. Same is true for the second recursive call. No matter how the input is organized, whether it's some bad case or some good case, its running time will always be T of n divided by 2. And remember the analysis in the merge algorithm itself, we haven't anywhere said this is what happens when we have such an input, or this is what happens when we have a good input or bad input. This C times n applies to any input of size n when the algorithm merge is working, because the initial for loops will require some constant times n, the last for loop will require some constant times n, right? No matter how the input is organized, this is the time that it will require, which means that the merge sort algorithm doesn't have two separate running time analyses like worst case and best case, which was the case for insertion sort. Unlike insertion sort, merge sort has a single running time, okay, which is described by the recurrence 2 times T of n divided by 2 plus Cn. So this is not the answer, but this explains something else. It explains us that merge sort has a single type of running time analysis. It doesn't have worst case, best case analysis. No matter how the input is organized, this will be its the recurrence describing its running time. Let's get back to our original question then. Why is it not enough to leave our running time analysis, to finish our running time analysis by saying that I have analyzed the pseudocode and I have found that the running time T of n of merge sort is equal to 2 times T of n divided by 2 plus C times n. Why don't we just finish it here? What else do we need to do? Does anybody remember from our discussion from yesterday? Okay, this is the inductive part. Base case, you can always assume that T of some constant, let's just choose 1, is equal to some constant. Again, let's just choose 1. Okay? Because for the base case, let's look at merge sort algorithm. The base case is that if left is equal to right, which means that there is nothing to sort, in that case, our algorithm simply returns what is the time spent if we have an input of size 1, then it's just simply constant time, because all we do is a single comparison, is left equal to right. And then we execute the return statement. So just constant amount of time. We can write any constant in here. For convenience, let's just write 1. So you are right, Faizenur. We always need to remember to write down the base case as well in a recurrence relation. So T of 1 is equal to 1 and T of n is equal to 2 times T of n divided by 2 plus Cn, where this inductive part applies to cases where n is greater than 1. But this is still not the answer we are looking for. So the question was, why don't we just leave it here? Why don't we just say that we have analyzed the running time and this is the recurrence describing the running time? Because by just looking at this recurrence relation, by just looking at this definition, we cannot tell how big or how small T of n is. Because just by looking at this, we cannot say whether Tn is theta n cube or n to the fourth or 2 to the n or n square or simply n, right? So we need to basically solve this recurrence relation. We need to find a way to describe this T of n in open form formula so that we can claim Tn is, for instance, n cube or n to the fourth or something else. Okay, so in our analysis of recursive algorithms, this is the way to follow. First, find a recurrence relation by reading the pseudocode, find the recurrence relation to describe the running time, and next step is to find an open form formula for this recurrence relation. Let's see now how we can do that part. So I'm skipping all this part. We have already discussed this part. Now, our T of n is equal to 2 times T of n divided by 2 plus some constant times n. This is the inductive part, and for the base case, T of 1 is equal to 1, for instance. How can we solve such a recurrence? How can we find an open form formula for such a recurrence? One way to do this is to work with a recursion tree. Okay. In a recursion tree, we start with our inductive part of our definition, and we try to expand each time these t terms. Okay. In a way, at the end, this will give us a tree where we will have terms defined without using t, and if we sum up all the terms in that tree, that will give us a guess regarding this t of n. Let's see how it works. For convenience, let's just assume that n is a power of 2. So we first start out by our initial definition. Tn is equal to Cn, so Cn in here, write it as a root, plus 2 T of n divided by 2. So in one branch, T of n divided by 2. In another branch, T of n divided by 2. Now, if I sum up all the terms in this initial tree, I should get Tn, because I have 2 Tn divided by 2 and also Cn. Now, from now on, I will try to do another expansion. In this expansion, I will not touch the Cn part because it already is expanded. It already is in open form. I will try to first expand this T of n divided by 2. How can I replace this T of n divided by 2? I will go and look at the definition of T of n. Okay. In the definition of T of n, if I replace this n, and this n with n divided by 2, I should get the definition for T of n divided by 2. So replacing n with n divided by 2 in here, it tells me that T of n divided by 2 is equal to 2 times T of n divided by 4 plus C times n divided by 2. That in my tree, I will simply write it down. So C of n divided by 2, that was the last term, and 2 T times n divided by 4. Notice that if I sum up the terms in this smaller tree in here, I get T of n divided by 2. Same goes for this other tree. This part, 2T of n divided by 4 plus C times n divided by 2 corresponds to T of n divided by 2. Now notice that now if I sum up all the terms in this tree, it still gives me Tn, because I have Cn plus each of these little trees corresponds to T of n divided by 2. So I have Cn plus 2 times T of n divided by 2. Now imagine doing this expansion for these terms as well, T of n divided by 4s as well, and then keep on doing those expansions. At the end, we will get a tree similar to this. In the first level, we will have Cn, this one. In the next level, C of n divided by 2, C of n divided by 2. Imagine expanding T of n divided by 4. We will have C of n divided by 4 at this level for each node, okay? And in here we will have, for instance, T of n divided by 8. And if we expand that, we will have C of n divided by 8s all over here, and so on. Now, looking at this tree, we will try to go over level by level and sum up all the terms appearing at a level. In the first level, the sum is Cn. In the second level, the sum is again Cn because I have two Cn divided by 2's. In the next level, I have again sum being equal to Cn. You can imagine that if we continue this, in the next level, we will again have Cn. Okay? So, in this tree, we have many levels, and the sum of the terms at each level is simply Cn. Remember that my original goal is to sum up all the terms in this tree, which means that I need to sum up all these Cn's. How many Cn's do I have in this recursion tree? It depends on the height of this tree. In other words, if we keep on expanding these T terms in this tree, when do we reach to our base case of n being equal to 1 or n being equal to 2, some constant? So the first term in here was T of n. The next level was describing, the node in here was describing T of n divided by 2. At level 2, we are describing n divided by 4. At level 3, we will be having T of n divided by 8. At level 4, we will have T of n divided by 16 and so on. So which means that at level k, we actually have T of n divided by 2 to the k. So this is T of n divided by 2 to the 1, T of n divided by 2 to the 2 to the 1, sorry, here. T of n divided by 2 square, T of n divided by 2 cube for the next level. Yeah. So which means that at level k, we are expanding T of n divided by 2 to the k. In this tree, in this recursion tree, at level k, we are expanding T of n divided by 2 to the k. Since at the bottom we have T of 1's all over in here, T of 1's, if we want to find out the level k that we reach to the bottom layer, to the leaf level, we need to say when does this n divided by 2 to the k become equal to 1. So n divided by 2 to the k, at what value of k does it become equal to 1? So, which means when does n become equal to 2 to the k? So when does n become equal to 2 to the k? If we take the logarithm of both sides, we will see that logarithm of n is equal to logarithm of 2 to the k, and by the rule of logarithms, we can write this one as k times logarithm of 2. Note that all logarithms are base 2, so this basically evaluates to 1. So we have log n is equal to k. So at k equals to log n level, we arrive at T of 1's, which means that the height of this tree, the number of levels that we have in this tree, is log n. Since we have log n many levels in here, and since each level sums up to Cn, the sum of all the terms in here will be simply Cn times log n, because each level sums up to Cn, and we have log n many layers, log n many levels in this tree, height being equal to log n. So our running time is some constant times n log n. And we can describe that running time with, forgetting about the constant, theta n log n. This is our guess for T of n described with this recurrence using the recursion tree construction. Is it clear how we arrived at this guess that this Tn in here is theta n log n? Is our example with the recursion tree clear? Can you all still hear me? Okay, so is the discussion clear? Do we need to repeat any part of this discussion? Any questions regarding the recursion tree? So let's sum up what we do in the analysis, in the running time analysis of an algorithm. We go over the algorithm itself. If it's a recursive algorithm, we first try to read the pseudocode and come up with a recurrence relation describing the running time. This is the first step to find out this recurrence relation. The next step is to find out a guess for an open form formula for this recurrence relation. One way of doing such a guess is through the construction of a recursion tree, basically through each time expanding these t terms and finding out the sum of terms in the tree. Using that for merge sort, we came up with the following guess that it is n log n. Now, is our job for our running time analysis over at this point? Not yet, because the bound that we find, this n log n bound or n log n function that we find corresponding to this recurrence relation is simply a guess that we have come up with using expansions in a recursion tree. Now, a guess is always a guess. In order to formally prove that this guess is correct, one last step remains, which is we can use now mathematical induction and the formal definition of the theta notation to prove actually that n log n is an open form formula for this recurrence relation of Tn. That would be the last step to prove using induction that the guess that you have found, the theta bound that you have found, is actually correct. We will do that later on, but let's first now concentrate on what the formal definitions of these asymptotic notations are. For instance, the theta notation or the big O notation. So far, we kept using this theta notation without giving an explicit formal definition. Let's now try to formalize our definition of these notations, of these asymptotic notation. As part of asymptotic notation, we will mainly have three common notation: theta notation, big O notation, and big omega notation. Let's start with the first one, theta notation. Note that each of these notations actually are notations that we use to simplify the description of the functions so that different functions will become comparable. Theta, each of these functions are asymptotic. Each of these notations are asymptotic notation, which will mean that they will simplify functions, assuming that the inputs to the functions are growing towards infinity. Now, what is the formal definition of the theta notation, or what does it mean to say that some function f of n is theta of some other function g of n? It means that g of n is an asymptotically tight bound for the given function f of n. Let's first look at its figurative representation. If f of n is theta of g of n, it means that arithmetic comparison operators, you can think of theta notation as being equivalent to the equals operator. So in some way, we can think of f of n being almost equal to g of n. Why? Because multiplying g of n with some constant, f of n is lower than that, is smaller than that, while n going to infinity. So this part is n, and this part represents the values of the functions. For really, really large values of n, if f of n is in between g of n and g of n itself, basically we'll multiply with different constants, then we will call f of n to be theta of g of n. So basically, we can represent f of n with g of n. Why? Because multiplying with a constant, f of n becomes smaller. Multiplying with some other constant, f of n becomes bigger. So basically, this means that we can think of g of n being almost equivalent to f of n. Formally, it tells us that there exist positive constants C1, C2 such that starting from some starting point n0, f of n is less than or equal to constant C2 times g of n and is greater than or equal to constant C1 times g of n. Okay, so this is the formal definition. If somebody asks you to formally prove that f of n is equal to theta of some function g of n, all you need to do is to find out special constants C1, C2, and N0 such that this statement becomes true, that f of n is less than or equal to C2 times g of n, also greater than or equal to some constant C1 times g of n. Any questions about this definition? So basically, with the theta notation, f of n is sandwiched in between g of n's. Okay? That's why we can think of this notation to mean almost equality. So as n grows to infinity, f of n behaves the same way as g of n. Notice this growth behavior in here. F of n is growing in some way. Well, some constant times g of n is growing the same way. Some other constant times g of n is also growing the same way. And f of n is sandwiched in between them. Is there anything we need to repeat regarding the formal definition of the theta notation? Is this part clear? So let's go name by name to see if everybody is still there. Asena, is this part clear? Okay, how about Chautai? Chautai, is this discussion clear for you? Okay, so now we have two more asymptotic notation that we need to discuss. But before that, let's see an example application of this theta notation definition. Remember that we previously, while talking about the worst case running time of the insertion sort algorithm, we came up with the following definition. We said that Tn looks like a function of this form. Some constant a1 times n squared plus some constant b1 times n plus c1. And we claimed that this is theta n squared. Okay? Now, how can we prove that this is true, that a1n squared plus b1n plus c1 is actually theta of n squared? To prove that, we will need to use this definition. We will need to find out constants c1 and c2 such that our f of n, in this case a1n squared plus b1n plus c1, is less than or equal to c2 times n squared and is greater than or equal to c1 times n squared. If we can do that, then we are done. So all we need to do is show that there exist constants d1, d2 such that our f of n, a1n squared plus b1n plus c1, is less than or equal to constant d2 times n squared greater than or equal to constant d1 times n squared, starting from some constant n0. Okay, so we pick special values for these two constants. If I pick d1 equals a1 divided by 2, let's see what happens. On this left part, we will have a1 divided by 2n squared, this part. And in the right part, we already have a1n squared plus b1n plus c1. Even if you forget these two parts, b1n plus c1, a1 squared is already bigger than or equal to a1 divided by 2n squared. So this part of our inequality is true. For the second part, we need to show that a1n squared plus b1n plus c1 is less than or equal to d2 times n squared. For this, we pick d2 equals 2 times a1. Is it true that a1n squared plus b1n plus c1 is less than or equal to 2 times a1n squared? Basically, how about now? Do you hear now? Okay. So let's continue where we were left off. For the right part of the inequality, we need to prove that a1n squared plus b1n plus c1 is less than or equal to d2 times n squared for some constant d2. We pick d2 to be equal to 2a1, and doing some math, we arrive at a1n squared minus b1n minus c1 is equal to 0. Now solving for n in here, it has two roots, these two ones, and we can pick and 0, our starting point, to be the bigger one, because after this root point, we know that a1n square will be greater than or equal to b1n plus c1, which means that after that point, this second inequality will hold. So we basically found out constants d1, d2, and starting point n0 such that our function f of n is greater than or equal to some constant times our g of n, which is n squared, and also smaller than or equal to some constant times our g of n, which is n squared, Okay, so this, although this is the formal definition of the theta notation, it's good to keep in mind some simplifying facts. So one of the things that this definition tells us is that we can actually forget about the lower order terms with the use of the theta notation. So let's inspect T of n in here. We have a1n squared plus b1n plus c1. The highest order term in here is a1n squared. With the theta notation, since theta notation is actually a notation that we use to simplify functions, it tells us that forget about the lower order terms. Forget about the term with n, since n squared is already bigger. And forget about the term with n to the 0, since n squared is already bigger. So now we have already simplified this kind of complicated function, a1n squared plus b1n plus c1, into a simpler term, which is simply a1n squared now. And the second thing that it tells us is that we can also forget about the constants that appear in the highest order term. So looking at here, we were left with a1n squared. Since a1 is a constant, it tells us that you can forget about this constant as well. So T of n, you can think of it as simply being theta of n squared. Is this discussion clear? Okay, does anybody have any questions regarding this last discussion? Let's just give as another example. So if I analyze the running time of some algorithm, and if I come up with the following complicated function, 3/7 times n cube plus 5/2 times n to the 3/2 log n plus 178. So let's say I analyzed the running time of some algorithm and I came up with the following Tn that describes this running time. With the theta, using the simplifications of the theta notation, I can forget about this constant because highest order term is n cube. I can forget about this part as well, actually, because n cube is already bigger than, asymptotically, it grows bigger than n to the 3/2 times log n. So I can forget about this part as well. So I'm left with this part, 3/7 times n cube. I can also forget about the constant multiplicative factor, 3/7. All I'm left with is n cube. So I can simply claim that the running time of my algorithm, Tn, is n cube. So if no further questions, let's go on to our second type of asymptotic notation, which is the big O notation. The big O notation will simply capture only one side of our theta notation. It will only be an upper bound and it will capture this inequality. More formally, if we say that f of n is big O of g of n, or in other words, g of n is an asymptotic upper bound. So f of n is upper bounded by GON. What we mean exactly is that there exists constant C such that f of n is less than or equal to C times GON for starting from some point n0. Figuratively, it tells us the following, that if I draw the C times GON as like this, then f of n will, after some point, will always be lower than GON. So this is f of n, this is some constant times GON. So figuratively, we are basically seeing this part of the figure. F of n is upper bounded by some constant times GON. And the omega notation is just the opposite. If we say that f of n is omega of GON, or in other words, that GON is an asymptotic lower bound for f of n, what we mean is that there exists constancy such that f of n is greater than or equal to some constant times GON. So for these notations, just so that you may maybe make a comparison with the arithmetic operators, you can think of the theta notation as being equivalent to the equals arithmetic operator, the big O notation as being equal to the smaller than arithmetic operator, and finally the omega notation as being equivalent to the greater than operator. So if I say that f of n is big O of GON, in some sense you can think of it as f of n is less than or equal to GON. Okay, so less than or equal to. And for omega notation, if I say that f of n is omega of GON, you can think of it as f of n is greater than or equal to some GON. There's just a very slight variation of these definitions as well, small O notation and the small omega notation, but let's just skip this detail. For now, let's keep our concentration on theta, big O, and omega. Whenever we analyze the running time of some algorithm, ideally we would like to find out a theta bound to describe its running time, because theta is a tight bound. If I claim that T of n, the running time of some algorithm is n squared, it basically tells me that the running time grows almost the same as the function n squared. Okay? But it's not the same for big O notation. If I say that, if I find out that the running time T of n of some algorithm is, let's say, n squared, it doesn't mean that the running time will exactly be growing like n squared. The running time of the algorithm actually might be much smaller. For instance, the running time might be simply log n. And that running time T of n is still big O of n squared. It's still upper bounded by n squared. So the bounds that we give with big O are upper bounds. But theta bounds are actually tight bounds. They represent almost the same function. Okay? So ideally, when analyzing the running time of some algorithm, we would like to find out a theta bound for its running time. If we cannot do it, then the next best thing to do is to find out a big O, at least an upper bound for that running time. Because in that case, we will know that the algorithm will have at most that much running time. It will not be any bigger than that. Okay. Any questions about any of these discussions that we have had so far today? Anybody else? So any questions so far? So is only Vladislav listening to this conversation? I hope that everybody else is also still online and listening to our lecture. Okay, let's try to now see a couple examples regarding recurrence relations, relations that we define in terms of Tn recursively, and trying to find out these bounds, the theta or the big O bounds for those functions, and finally trying to prove that our guesses for those TOVANs are correct. So for that, I will open another slide. So the computer is a bit slow. We'll need to wait, I guess. Okay, so here it comes. Let's see some examples of solving recurrences. We have seen that if we have a recursive algorithm, we first describe its running time recursively as well using a recurrence. Basically, T of n is equal to something. And then the next thing to do would be to solve that recurrence, basically to come up with an open form formula for T of n. Or equivalently, we can try to first of all find a theta bound for T of n. If not possible, maybe we can find out a big O bound for the given T of n. Now, how to do this? How to find out, let's say, a theta bound for a recurrence relation T of n. As we have mentioned before, one way is to use the recursion tree, or another thing that we could do is from experience, maybe we have seen some recurrences similar to the one that we are working on currently, and they look similar. If that's the case, using either that kind of experience or trying to draw a recursion tree for the T of n, we guess a solution. Okay. Note that the sums we find from the recursion trees are also guesses. And the next thing to do would be to prove that our guess is correct using induction. One thing to note that if we are describing running times with T of n, we can always assume that this n is an integer because it will denote us the size of any generic input to any algorithm. And we can assume that that size is always a positive integer. So Veli has asked if I will ask the PDF slides. I'll see. So you can actually, we are recording all the videos. Okay. So you should try to download all the videos that we have recorded so far as soon as they are available. And in those videos, the PDF slides should actually be clearly visible. But I will think about it. I may also share some pages from the slides as well. But normally the videos should actually capture almost all the things that we already discussed. So let's see some examples of how we solve recurrences. So by the way, this is called the substitution method. So you basically try to make a guess using a recursion tree, and then using induction, you try to prove that your guess is correct for solving this recurrence relation T of n. As an example, let's consider the following recurrence relation. Let's say that, well, does anybody recognize this recurrence relation? So T of 1 is 1, and for the inductive part, T of n is 2 times T of, this is, you can forget about this detailed notation, it's just the floor function, 2 times T of n divided by 2 plus n. Do you remember this recurrence relation? From where? Yes, we solved in the previous example, so which was actually the recurrence relation describing us the running time of the merge sort algorithm. Okay? Yes, merge sort. Remember that for this recurrence, we constructed our recursion tree, and then we summed up all the terms in our recursion tree, and we have come up with a guess that this T of n is equal to theta of n log n. Now it's time to actually prove that that guess is correct. Okay, so let's say given this recurrence, we want to prove that T of n is, let's not go into details with the theta. For now, let's say that we want to prove that T of n is big O of n log n. Notice that if I prove that T of n is big O of n log n, and I also prove that T of n is big omega of n log n, that means that T of n is theta of n log n, because theta means that the function itself is at the same time upper bounded and also lower bounded by the given g of n. Okay, but for now, let's say that given the recurrence, we want to prove that T of n is equal to big O of n log n. We came up with this guess already using recursion tree. How do we now prove it? In the first couple of slides, I'm working on with other guesses, but let's just see the actual guess. So this is our guess, T of n is big O of n log n, and we want to prove that this is true for our given recurrence relation. Let's first write down the formal definition of big O. If we say T of n is equal to big O of n log n, it means that we mean T of n is smaller than or equal to some constant c times n log n, starting from some n0. Okay, this is the definition of big O. Now, this is the main claim that we have. Given the recurrence, 2 times T of n divided by 2 plus n, T of n is less than or equal to some constant times n log n. How can we prove such a claim using induction? Remember that in our proofs by induction, we have our inductive hypothesis, which is basically we assume that the thing that we want to prove, the claim that we want to prove, is true for some values smaller than n. So in this case, for the inductive hypothesis, let's assume that the claim that we want to prove is true for n divided by 2. In other words, let's assume that T of n divided, replace n by n divided by 2 in here. In other words, T of n divided by 2 is less than or equal to c times n divided by 2 times log of n divided by 2. Because this is what we want to prove for n. Let's assume that this is true for n divided by 2. Based on this assumption, let's prove that the same is true for n. That is, T of n is also less than or equal to c times n log n. Does everybody recognize this format from your discrete computational structures courses where you talked about inductive proofs? Basically assume whatever it is that you want to prove for a smaller instance, in this case for n divided by 2, try to prove the same thing for n. Okay, now using this inductive hypothesis, we first take our recurrence, the definition of our recurrence, which is T of n is equal to 2 times T of n divided by 2 plus n. Now at this point, we use our inductive hypothesis and replace this T of n divided by 2 with this term, C times n divided by 2 times log of n divided by 2. Why can we replace it? Because of this inductive hypothesis that we make. We are assuming that T of n divided by 2 is smaller than or equal to C times n divided by 2 times log n divided by 2. Now, continuing with some simple math, what do we have? We can just forget about these floors because they are just some details. So now we have 2 times Cn divided by 2 log n divided by 2 plus n. 2's will cancel. And remember that log of n divided by 2, we can write it as logarithm of n minus logarithm of 2. So this will be Cn. So Cn times log n minus Cn times log 2 plus n. Since logarithms are always base 2, logarithm of 2 will simply be 1. So we will have Cn log n minus Cn plus n. Remember what we wanted to prove? We wanted to prove that T of n is less than or equal to Cn log n. So is this term smaller than or equal to Cn log n for some value of Cn? Now if we simply pick C equals 1, these two will cancel out and we will have Cn log n less than or equal to Cn log n, which is what we wanted to show in here. Based on our assumption that T of n divided by 2 is less than or equal to Cn divided by 2 log n divided by 2, we wanted to show that Tn is less than or equal to Cn log n, and that's what we did in here. Finally, this is the inductive part of our proof, inductive component. We need to prove our claim using base case as well. Remember, this was our main claim. We need to show that with our recurrence, we had T of 1 equals 1. Now, is it true that for n equals 1, T of n is smaller than or equal to Cn log n? This is for the base case. T of 1 is equal to 1. Is this smaller than or equal to Cn log n for n equals 1? For n equals 1, if we replace C times 1 times log 1 is 0. So we have 1 less than or equal to 0, which is not true. Okay, so this is a slight problem, but it's not a big problem because remember that T of 1 is our base case for the recurrence. And it seems that T of n less than or equal to Cn log n doesn't work for n equals 1. It's not a big problem because we can always change our starting point n0. Rather than picking n0 to be equal to 1, we can pick something else. So let's pick, for instance, n is equal to 2. So if we have T of 1 is equal to 1, according to this recurrence, we have T of 2 is equal to 2 times T of 1. So basically 2 times 1 plus 2, which is 4. So T of 2 is equal to 4. Is our claim that T of n is less than or equal to C times n log n true for n equals to 2? For n equals to 2, we have C times 2 log 2. Log 2. So we have 2C is 4 less than or equal to 2C. If we pick C equals to 2, this will hold. But leaving with only base case being n equals to 2 is not enough, because we will have, so instead of this base case, we now have t of 2, but then t of 2 is the base case. For t of 3, it is defined by this inductive component as well. So it is equal to 2 times t of 1. So since our claim is not true for t of 1, we need to explicitly include n equals to 3 into our base case as well. So t of 3, according to this definition, if we replace it in this definition, it is equal to 5, is our claim that 5 less than or equal to c times n log n, for n being equal to 3, true in this case. This is also true if we pick c equals to 2. So these two together make up our base case, and we can now see that since this claim that t of n is less than or equal to c n log n, both for our base cases and also for our inductive components, then finally we claim that t of n is big O of n log n. So this discussion in here is a simple application of mathematical induction, which I assume that you must have seen many examples of in your discrete computational structures course, as applies to the definition of big O and the recurrence definitions. Any questions about this discussion? We would see some further examples, but I've already set up this meeting to finish at 3:40, so we have 2 minutes that are left, so we won't continue with further examples. We can see further examples sometime next week, and for next week's lectures, we can make each one, both the lecture on Monday and also the lecture on Tuesday, maybe 5 or 10 minutes longer, so that we can make up for the lost time that we have had today due to the malfunction in my computer. Okay, so let's make Mondays or Tuesdays course lectures a bit longer, 5 or 10 minutes longer. Do you have any final questions regarding the discussion we have had today? Seven o'clock. All right, bye.